Okay, we're going to conclude our discussion of section 3.6. Before we do that, take a look at this warm-up and pause the video and spend a minute doing those. Spend perhaps a few minutes doing these. These are not insignificant problems. I won't give you any hints, but you're going to apply the methods that we learned in the 3.6, the first part of this lesson that I taught, and let's see how you do. They can be a little bit involved. So pause the video. All right, let's take a look at the solutions here. I'm not going to go through the details of the solutions, but just check your answers. This is the answer to the first one, and this is the answer to the second one. By the way, there's another kind of funny problem in the corner for you to do. That's not really part of what I need you to do. I just put that there because it'd be fun for you. So give it a try. But you can see that perhaps you could solve it using some of the techniques that we've been learning. So in these problems, just to remind you quickly about what we learned in 3.6, you'll recall that what we did is we found first the solution to the homogeneous equation. So for example, in this first problem, we found the solution to this equation right here as if there's a zero here. That appears right here, right? So in the end, our solution will be a combination of first the homogeneous solution and then the particular solution, right? It's like the sum of those two things. And so the second half is what we get by making an assumption that the solution that appears here will take on the form a x squared plus bx plus c. Why? Well, because that's the undetermined coefficients set that we're going to use for x squared. Remember, we're going to use it, this function, this non-homogeneous term, it, and all of its derivatives, or rather kind of a linear combination of those things. And then the goal is to take it and its derivatives, plug them in, and then figure out just by corresponding the coefficients what those coefficients need to be. In this situation, it'll end up being you solving a system of three equations in three unknowns. So go back and look at the first video for context on that process. For B, the same kind of thing is true. Solve the homogeneous equation first. You'll get this. That is, pretend this is zero. And then solve the particular solution. It's quite easy here. It's just going to be the only thing in your UC set is going to be like A times e to the 2x. So you'll put that in as your, and put it in and then put its second derivative in, collect like terms, and then you'll pretty quickly get that the constant a, they're not really a system to solve. The a needs to be 1/13. So we're going to finish 3.6 today, and we're going to, in particular, we're going to do two things that we didn't maybe get to in the previous lesson video. I want to take a look at particular solutions of initial value problems. I think it's fairly straightforward, but we want to maybe mention those. And then also a very important snag that we need to cover. So just to recap from our lesson and from the warm-up, we just said it. We've got the solution to these kinds of equations where there's a non-homogeneous equation where you have some non-homogeneous term on the right side. That's what that g of x is there. It's going to be the sum of the homogeneous solution and the non-homogeneous solution. We just mentioned that in the warm-up. Also recall that different authors have different names for these. Sometimes you'll hear people say the complementary solution and the particular solution. The homogeneous solution is found using the characteristic equation from techniques earlier in this unit. And then right now, although we're going to give you another method as well, the particular solution can be found using the method of undetermined coefficients. So let's use this problem to recap here. So first we're going to solve the homogeneous differential equation, and feel free to pause the video and try really the whole problem, including the initial value problem if you'd like. And I'll pause the video and I'll see you again in 5 minutes or however long it takes you. Could be a little bit involved. There's a number of steps here. Okay, so let's jump into it. First we're going to solve the homogeneous equation, pretending that the right side of that equation is 0. As we do that, we're going to get this for the solution. I won't go through the details of solving that homogeneous equation, but you're going to write down the characteristic equation. It's a quadratic. You'll factor it, and it'll admit in this case, two distinct roots, and so that's the homogeneous solution. Now we're going to take a look at that function on the right side. It's a combination of what two functions? Looks like we've got like an x in there and an e to the something. It's like a linear times an exponential. So the UC set we need for the x is just simply like x and 1. The UC set for e to the 2x is e to the 2x. And we're going to need, and so those are the combos. The combo of those things is going to be the product of each of the sets with all the others. It's not obvious from this, but if you have like a UC set that has 3 elements and a UC set that has 2 elements, then the UC set combined will be 6. We're going to need like all of the combinations of all the things, right? In this case, it's just that, though. You could write it in its factored form as well. All right, so now we have a form for our particular solution, and now we just need to use it together with its first and its second derivative, and we'll plug all those things in to our equation, our original differential equation. So here we go. It's going to look a little messy for a second, but there goes purple, blue, and red. And now, hopefully you've had a chance to try this problem, but if you haven't and you're trying to catch up, what are we going to do next? We're going to collect all of the things together that have like terms. So on the left side, when we collect all the things that simply have an e to the 2x, we get the coefficient negative 4a plus 3b. And all the things that have an x e to the 2x, that's just 3a as we collect all those like terms. And now we can compare those with what's on the right side. And notice that I've included e to the 2x on the right side, even though it's got a coefficient of 0, just so that we can have kind of an honest comparison. This is a system of equations, of 2 equations and 2 unknowns, but really it's not, right? Because 3a equals 9 gives us what a is immediately. So it's hardly a system at all. So as we do that, we combine those solutions, find the constants, and then put them in here. So we've got our particular solution, and now we've got an IVP still to solve. Whew. So we're going to need to use both the first and the original function and its first derivative. So there they are. And now plug in the initial condition if x is 0, y is 5 on the left one. And on the right one, if x is 0, y prime is supposed to be 10. So making those substitutions and cleaning it up gives us, that's right, another system, a system involving C1 and C2. So there they are, those 2 equations that appear at the bottom of this slide right now. Together, we'll admit the values of C1 and C2, solve using your favorite method. Whew! And you'll get that. I'll skip the details, but maybe substitution would do it pretty quickly for you. And finally, return to the original solution that we had and apply those two constants. So there we go. We have it. The final solution to the entire non-homogeneous equation with its initial conditions applied. Okay. Now, are you ready for a snag? Well, it doesn't seem like there's anything wrong with this problem. This seems pretty innocuous. I mean, feel free to pause the video and start hammering through it. You might even solve the whole thing and not realize that there's something amiss. But right here, if you're paying attention, as soon as we write down the solution to the homogeneous equation, take your time to find it, right? Find the characteristic equation. It's a quadratic. Factor it. It's got 2 distinct roots, so we got 4 and -1, so you plug those in as your exponents. So we're good to go. Everything's just great. But here's the issue. If we let our yp be a e to the negative x, that's I think what everyone would want to do. Take a look on the right side. Isn't that what we do? And we take the first and we take the second derivative. Everything's feeling great, right? We're going to plug those in. But as we plug this in, notice that that's repeated in the solution we get. So if we use this as the particular solution, right now, what are we saying? Since it's part of the homogeneous solution, you tell me, what happens if we right now plug in a e to the negative x into the left side? What are we going to get? I'll give you a hint. It's not 2e to the negative x. The thing you're going to get is 0, because we know that anything of the form something times e to the negative x, that's part of the homogeneous solution. So the thing it gives you if you plug it in on the left side will give you on the right side 0, no matter how hard you try, no matter what you select for the letter A. So that is like, although at first we were excited about this is a real problem. So here's what we're going to do. You can see here, this just gives you 0 if you do that. So this isn't working. So what we're going to need to do is we're going to need to revise the UC set. And the technique we're about to use, well, it's a pretty familiar one by now. We've thought about this before, and it gives way, this idea of multiplying by an x gives way to a more general principle that this kind of always works to fix the UC set. So we're going to try, instead of a e to the negative x, we're going to try x times e to the negative x. Now we don't need to include its like the forms of its derivatives, because in this case we already know that that's going to be included in the homogeneous solution. So we're not going to, normally if you saw that as your UC set, you'd be like, oh wait, you need x e to the negative x, but you also need e to the negative x. But we already kind of covered that, right? That's already going to be in the homogeneous solution. It's not going to give us any added benefit to have it in there. I mean, it wouldn't hurt, but it's not needed. So there's our revised UC set. Let's see if this does the trick. So y prime and yp double prime using the product rule are there. And now we can see as we substitute those in, it's going to take us a second to, as usual, collect like terms. If we collect like terms here, we see that negative 5a needs to be 2, that coefficient on e to the negative x. I'm just looking through there and looking for things that, not x e to the negative x, but things that have an e to the negative x as what they have. So here, I'll highlight those real quick. We're looking for this guy right here. This guy right here, negative 3a will be what that is. And that's it, right? Just those two. Solving for a gives that, and we're done. So, okay, disaster averted. That's not too bad, Mr. Chase. I thought you said it was a significant snag. Well, I hope you think that wasn't too bad, but just something to really, really pay attention to. We'll give you some that are a little more challenging as we move forward. Let's take a look at this one. And already you can kind of see what's lurking, probably, right? Go ahead and stick, actually, just inspired by the last slide, maybe you want to give it a try. Hit pause if you want to try it on your own. Okay. The homogeneous equation gives this as its solution. Remember, the characteristic equation here is r squared plus 1, which has its roots are negative and positive 1. And so we've been through that before. This has that simple form for its homogeneous solution. Now, looking at the right side, the cosine x is not going to do here, right? That's normally we would say, oh, the UC set's going to be cosine and sine. But the same issue arises that happened in the last one. If you were to do this, if you plug in this particular solution and its derivatives into our equation, you're going to get 0, right? Because it's just, it's part of the homogeneous solution, which if you give me something that's, no matter what a and b are, if you plug that in, that's the whole point. The homogeneous solution gives 0, not cosine. So that is not going to work for us. I hope you understand that logic, why that's just not going to cut it. Feel free to give it a try. Plug it in. You'll see, of course, you get 0. It doesn't matter what a and b are. So we're going to take the play from the book that we just talked about on the last slide, the last example, multiply by x. So this is going to be what the form of our particular solution is going to be for this problem. And again, at any point, feel free to pause and kind of see if you can beat me to the punch here on your own paper. All right, let's do the setup for this. You can see there's a lot going on there. This is just to prove a point. So take a look and see if you can figure out how to set that up. Again, pause the video and see how you do. Don't solve, though. It would be a little bit much. Okay, so the first thing you notice is that if you're going to do this correctly, if you're going to like write down the form of the particular solution, even if that's all someone asks for, hey, I just need the form of the particular solution. If that's all they're asking for, you still, even if you're unprompted to do so, you still have to find the homogeneous solution, right? So normally we'd just be like, oh, it's x squared, x1 e to the x e to the x e to the x, and e to the 3x. Okay, so that's kind of what we need. And so that would be our first guess. It's just like, throw some constants on all those things, you know. But wait, it says, but wait, if you look at the homogeneous solution, you'll see that it has the form C1, e to the 2x plus C2 e to the x. So let's now kind of look for overlaps between that and our UC sets that are in those red boxes. So what do we see? Well, e to the 2x is kind of safe, right? So we're okay with that. It doesn't overlap at all. But e to the x does overlap. And so there's only one offending set here. You don't have to multiply all of these by x, right? Don't multiply all the red boxes by x, just the offending box. So in this case, there are kind of two offending boxes, but that whole box right here needs to be multiplied by x. So we're going to get an x squared. The other ones don't. Now this one, by the way, we didn't really even need to mention this one, right? Because it's kind of included in this one. So really we're just looking at this set, and this set. And this e to the x really has nothing to do with this set or this set. So don't bother messing with these. This can stay as it is. This can stay as it is. But this set right here, we need to multiply by x, both things by x. So do it. When you do it, this is now our revised guess in blue. So we're gonna what we don't need again is that e to the x term anymore, because we know that that's going to be kind of subsumed in the homogeneous solution. So it would be superfluous to kind of have that e in there. I mean, you're welcome to. It won't hurt, but e is going to, I'll just tell you right now, e is going to be anything you want, right? So let's try just this kind of idea of set up but don't solve on all of these. Again, take a moment to pause the video. By the way, I've already done the work, not because I don't feel like you have the skills to do the homogeneous solution. I'm sure you can find the homogeneous solution. I just wanted to save you the time. So the homogeneous solution has already been written down for you on each of these. Take a moment to do this. And when you're ready, let's talk about how we might go about these. So looking at the right side of part A, our first guess would be, okay, well, we need AT, that's plus B. The AT plus B is me considering like the polynomial portions of this like 7t and this minus 1, right? Like that kind of takes care of that part. And then we've got e to the negative 7t, so I got another constant for that. Perfect. But wait, that's just a first guess. Let's take a little close look at this and think about the overlaps. We've got e to the negative 7t. That's going to cause a little bit of a problem. So we just need to multiply that by t. Notice that I didn't do anything to the AT plus B part. How about the second one, part B? What do you think? So again, if we're just making our first guess, we're just going to look at this. Boy, we've got a lot of things to think about here. We've got this guy, and then we've got these two here. So we've got a bunch of constants. Thank goodness that we're just setting up but not solving. All right, that's just our first guess, but let's make sure we understand even where our first guess came from. This term generates, obviously we need something of this form. We need something, as we take derivatives of this, you're also going to get things that involve like a t times e to the 10t. And you're also going to get, after taking a second derivative, you're also going to get things that have just an e to the 10t. So that is represented all captured here in this term. For the cosine and sine, we're going to need this e to the et plus f cosine t plus gt plus h sine t because of this t term here. And now the offending set here is this polynomial here because it overlaps with this e to the 10t. This doesn't matter, but the e to the 10t part of our homogeneous solution is a problem. So we're going to multiply that by t, and now we are good to go with that revised guess. Look at the little piece in red. Just that t is all we need. Take a look at the next one. Did you get this as your first guess? Whew! Again, glad we don't have to solve for the constants. So, sorry, there's like a lowercase d there. I don't know what happened there, but okay. Take a look at that. Does that comport with what you have on, is that the same thing you have on your paper? We got e to the negative 2t times all that. Got a and b. Okay, that's looking good. So what could be the problem? We'll look at the homogeneous solution. Looks like we've got some overlap. We've got cosine t over 2 and sine t over 2. which appears as part of what you're seeing here and here. We're not too concerned about this part because it's got the e to the negative 2t. So our revised guess just involves us multiplying the second set of stuff by t so that we don't get that overlap. All right, I've got two more for you. Again, pause the video. Are you getting good at this? And then let's check our answers here. Oh, I think, was that the problem we just did? I apologize. Oh, no, there's a slight difference there. The homogeneous solution on the left side I gave you is something a little different. So there's a different overlap there. This time I'm going to need to multiply t by that the first set of stuff. All right, and then on the last one there, careful, there's something very sneaky on this one. Are you fast forwarding? Stop, pay attention. This one's important. This last example is important, really important. Okay, so take a look. Everybody's happy with that. That's our first guess based on by the first guess I always mean just kind of like just looking at the right side of the equation, like not even considering the homogeneous solution. So that's what I would write down if I just didn't even know what the homogeneous solution was. I'd be like, okay, well, how about that? Right, why? Well, because we've got e to the negative 4t times t squared, and we've got some things that have, I don't know why the terms have not been combined here, but we got like some stuff times e to the negative 4t. So it and its derivatives will have this form. But now let's take a look at the homogeneous solution. We've got an e to the negative 4t. So let's multiply through by t. Yay, everything's fixed, right? No, wrong. Well, because why? Well, because notice if we do that, that's good. This is no longer part of our solution. But notice the homogeneous solution actually has this as part of it too, because the homogeneous equation had a repeated root in it. Oh man, it's getting crazy, Mr. Chase. And because of that, this still has some of the homogeneous solution in it. If we have as t in here, it comes over to here times this c e to the negative 4t, we're going to get ct e to the negative 4t, and that is still part of the homogeneous solution. So you guessed it. What are we going to do? We're going to make a final revision. How about t squared instead? And that will ensure that no part of this will be something that is contained in the homogeneous solution. That's what's going to do the magic for you guys. All right, with that, thanks for listening to the second half of our 3.6 lesson. Sorry I went through that kind of quick, but it's a video, so feel free to pause and rewind and rewatch over and over again to your heart's content. Some more resources, of course, as usual, on this last slide. Thanks, you guys, and have fun solving differential equations.